2. What about the rest on this side? Eight. Okay. Okay. How many people? Eight. Okay. The majority. So who doesn't say A? Who says it's not A?
No, I can change to A.
So is everyone A?
Yeah.
So can one of the people who says A come and demonstrate why it is A? Maybe those who are closer to the I.
Okay, it's easy because delta ij requires that I and j to be equal. So the only two terms will be I and j is equal to 1 and I and j is equal to 2. So
Okay.
you just plug it in and you get answer.
Okay. Convincing. So yeah, Vasif said there is R11 squared plus R21 squared, which is cosine squared of theta plus sine squared of theta, which is 1. Okay, now if we calculate the whole matrix, this whole matrix is going to be, let me write it again. This whole matrix is going to be what? It's going to be the unit matrix. It's going to be this delta. And so I didn't define delta ij. I guess I didn't define. So this delta ij is called Kronecker delta. So it is 1 if I is equal to j, and it's 0 when I is different from j. And so in matrix notation, it is just a diagonal matrix with 1 sitting on the diagonal. In the 2D case, it's just a 2 by 2 matrix. So it's going to be just 1, 1, 0, 0. In higher dimensions, there will be more 1s on the diagonal and 0s everywhere. Okay, so okay, this was so far the review of Euclidean geometry. Now we want to talk about the space-time. And see how these the same questions can be asked in the case of a space-time when we have t and so one time direction and one shot spatial direction. Now let's for the moment focus on the two-dimensional 1 plus 1 dimensional space, and one time and one space component. And again, we can consider 2 points. Now 2 points in a space-time, they are usually called events. And now instead of R, I'm going to use X. So it's X and its components are also T and X. But I hope you distinguished it. So there is TA and XA. So let me put an index mu here. So here we were putting index I, which would run from 1 to d. Here, if we are talking about space-time dimension d, then mu will go from 0 to d minus 1. So d minus 1, the spatial dimensions are one time dimension. So x0 is all this time, and then I will be what I used to call R. And then we can now in the special relativity we have the speed of light. So now we can construct an invariant distance similar to this case, but now including the time. So now I can talk about IAB, which is C squared TA minus TB squared minus minus RA minus RB squared. So this is what we call the invariant interval in a space-time. Notice the difference. Now there is a minus sign here, so time is different from space. And I said C equal to 1 from now on. So then it becomes just TA minus TB squared minus the Euclidean distance. And we can use our matrix notation and write this as eta mu nu times xa minus xb mu xa minus xb mu. Okay, again the same summation convention is followed here. So these mu's that are repeated, they will be summed over, and eta is the Minkowski metric. So it's defined as follows. Eta is equal to -1 when mu is equal to nu equal to 0, and it is 1 when mu is equal to nu is equal to 1 to d. So when it is a spatial index, and then it is 0 otherwise when mu is not equal to nu. There will be a minus sign here with this convention. Okay, now we can ask the same questions. Now we can ask the same questions as before. What are the space-time transformations that preserve this interval IAB? Okay, so there are two obvious ones that I just follow from the previous discussion. Clearly, translations are still part of those transformations. So if I take x mu, x prime mu to be equal to x mu plus some constant a mu. By the way, these objects with mu indices are called 4 vectors. If you are in 4 dimensions, here I'm in 2 dimensions, 1 plus 1, so it will be a 2 vector. So these are translations which obviously preserve this invariant interval because again they cancel, A cancels from the difference. So this is easy. Again, we will have rotations. Which, what they do is that they don't change time, they only change the spatial component. So x prime 0 is going to be equal to x0, and x prime I is going to be some rotation matrix Raj times xj. Then what happens is that the zeros component of this doesn't change. This term, well, let's look at here. This term obviously is invariant because it's just the difference of the zeros, the time components, which are unchanged by the rotations. And then this term is our Euclidean distance that we discussed before. So since rotations keep Euclidean distance invariant, this term remains the same, that one remains the same, therefore the interval is not changed. Okay, so these are the things that we already had before. Now the new thing are the boosts, which when combined with rotations, they give us the Lorentz transformation. In particular, if I'm in 1 plus 1D, there is no rotation, right? There is no spatial rotation because the I here has only one index, I, sorry, 1. So I cannot rotate x to anything else. But there will be boosts. Even in 1 plus 1D, and those are just the familiar objects, x prime equals gamma x minus vt. So we would like to do something similar to here, to adopt some matrix notations to show this transformation. So we want to write it as x prime mu equals lambda mu nu times x nu. So we want to determine what are the components of this lambda. And again, if I compare this with these transformations, then we get the following expression that lambda mu nu is equal to, there is gamma minus gamma v minus gamma v, and now let us ask the same question as before. Let's ask, what is this object? If I take this boost and look at this quantity, let's ask what we get. In particular, let's see what is the 0, 0 component of this. Oh, let's wait for 1 minute. Okay, how many people say A minus 1?
Yes.
How many people say B? No one says B. Who says C? No one. Okay. So yes, the correct answer is minus 1. And again, the way we can show it is that so it's just using the summation convention. There is eta mu nu is diagonal, is non-zero only when mu and nu are the same. If mu and nu are 0, then we get lambda 0, 0 squared. And if mu and nu are 1, so we are here. Sorry, there will be a minus because so there will be eta 0, 0 plus eta 1, 1, lambda 1, 0 squared. And this is minus gamma squared plus so this is 1, 0, and by the way these are, so this is 0, 1, 0, 1. So this is gamma squared v squared. Oh, by the way, I didn't define gamma, so you couldn't even answer it. So this is gamma squared times minus gamma squared times minus v squared, which after defining gamma is equal to minus 1. Okay, and in general, So what happens in general? In general, if I look at eta mu nu times lambda mu alpha lambda mu beta, that is going to be eta alpha beta. So the 0, 0 component of this object is -1, which is just the zeroth component of eta, the Minkowski method. And in general, that you can verify that it's the case. Okay, so there is some, when we have this interval, but let me mention some other thing. This lambda, so I denoted boosts by lambda. We can also put these rotations inside lambdas. In other words, a pure rotation can also be written in this 4-index format. So if I have more spatial indices, then I have this lambda which has more components. So it's gonna look like some matrix that has zero components. So here we have gamma minus gamma v. Now if I have more spatial indices, say I have 2 space dimensions, there can be vx here and minus gamma vy, and here again gamma vx minus gamma vy, and then what sits here in this spatial part, that is a rotation matrix, Rij. And as we saw, these rotation matrices also leave the interval invariant. So in general, every transformation that has this property can be decomposed into a combination of a pure boost and a rotation. Okay, so let's talk about the properties of this interval that we defined, the Lorentzian interval. So that interval, unlike the Euclidean distance, which was R squared, this interval is not sign definite. So this R squared was always positive. So if I consider 2 points on a plane, the distance between the 2 points, or the distance squared, is always positive. Here there is this minus sign, so there are 2 possibilities, or 3 possibilities. It can, that interval can be positive, 0 or negative, and depending on that, the 2 points A and B have different causal relation. So what is the causal relation? If the 2 points, so let's say I put point B at the center, at the origin. So this is my point B. Now if the point A is within this, so, and I have set C to 1, and these are the lines with t equal to x and t equal to minus x. So if the point A is inside this region, then we say that the A and B are time-like separated. Similarly here, so these are time-like. This is also time-like. These points which are time-like, in this case, when A is a larger t than B, we say that A is in the future. If A is in here, this will be past. And then if A is inside this region, we say that they are space-like separate. Now, what Lorentz transformations do, they are kind of similar to rotations in the sense that if I remember in the case of rotations, if I had a point, so if I sit one of the points at the origin and then the other one is here, I can do rotations. By doing rotation, this point can move in the plane. So that's the orbit of a rotation. By doing rotations, I can move it in any direction in the 2D plane. So Lorentz boost or Lorentz transformations are similar in the sense that they move this point within this 2D plane. However, they do not change the causal structure, obviously, because they have to preserve that invariant interval. So therefore, since the causal structure or causal relation was defined in terms of invariant interval, that cannot be changed by Lorentz transformation. Therefore, Lorentz transformation do not move a point that is in the future region to pass or to the space-like region. So the orbits of Lorentz transformations are things like this. They do not mix these regions. Therefore, it's meaningless to say two events or 2 points are time-like separated, or they are space-like separated. They are not coordinate-dependent statements. Now, in particular, what we can do now, again, let's go back to the Euclidean case. What we could do here was that we could always set the y difference of 2 points to 0 by an appropriate rotation. So if point B is at the origin and point A is here, we can choose a new coordinate system in which y prime A is equal to y prime B. We can always choose a coordinate system in which this is true. The 2 points are aligned the x direction. And we just need to do this rotation. Now, in the case of Lorentzian geometry, what we can do is that we can always, if 2 points are time-like separated, we can always make them to sit at the same point. And if they are space-like separated, we can always make them simultaneous, meaning that we can make them to happen at the same time. So for instance, here, what would be the way to find, what would be the rotation that makes y a prime equals to y b prime? So what we learned was that y a prime minus y b prime was equal to y a minus y b times cosine theta plus x a minus xb times sine theta. So if we want this to be 0, that tells us what is the rotation angle. The rotation angle that does the job is given by tangent of theta equal to minus ya minus yb divided by xa minus xb. So similarly, for given the coordinates of the points on the plane, I can choose appropriate Lorentz transformation that makes them sit at the same point in the time-like separated case, or be simultaneous in the space-like separated case. Okay, any questions so far? then let's talk about this problem about Alice, Bob, and Charlie. Then we can go. Okay, so you have the notes or
Yes.
not?
Yes.
Yes.
Oh, I guess I didn't have your emails. So I have some lecture notes, and there are some problems in those lecture notes that I can that I suggest you have a look or read them, depending on how much interested you are before coming to the class. But okay, so the question is the following: we have three guys, Alice, Bob, and Charlie, and so what happens is that they meet, then Bob meet at the bar, for instance, or meet here. Then Alice and Charlie start moving away in the same direction, but along the same line, but in opposite directions with constant velocity. So Bob is at rest. There will be some VA and VC. And we want to just draw some space-time diagrams. So the first thing that we want to do is to talk about the word line. So far I talked about events, which are points in a space-time. Now if I have some observer or somebody who lives, obviously it will have different, so for instance, I have different positions at different times. So, or Alice has different positions at different times. But let's talk about Bob. So if I look at this two-dimensional space-time diagram, that observer that defines a line or a set of points, a continuum of points in this space-time diagram. And that is called a word line. So for Bob, it's going to be, since it is just staying at rest, it's going to, its word line is going to be just the t-axis. For Alice, since it is moving, the points, the set of points that define its location as a function of time, they form a line. And then for Charlie, it will be another line. And these velocities are subluminal, which means that they both are, the slope of both these lines are larger in magnitude than one. Okay, so these are the word lines of Alice, Charlie, and Bob. So what do we want to do in this? First of all, we want to define the proper time. So again, let's go back to the Euclidean geometry on this plane. So in Euclidean geometry, we define the distance between 2 points. But we can also define something else, which is the length of a curve. So imagine I have, instead of this interval, I am drawing some curve here. So we can talk about the length of this curve. That length of the curve is not the length of the straight line that is stretched between the 2 points. It's something different. How is it defined? It's defined by dividing this curve into little pieces and calculating the length of those little pieces using the Euclidean distance. Or imagine if I am talking about the distance between Trieste and Venice. That is, when we say, for instance, it's 200 kilometers, that is not the length of the straight line between the two. So there will be, like, if I look at the map, it's gonna look like this, I guess. And then there's Trieste here. And there is Venice. So there will be a road that goes from Trieste to Venice. And then we say that this distance, LTV, is equal to 200 kilometers, for instance. That is the length of this curve. So how do we calculate it? We just divide it into little pieces. Every small piece in the limit that this piece becomes infinitesimal, that becomes a straight line. We know how to calculate the length of a straight line. Then we sum it up or integrate. So then this LTV is just the integral from T to V, Trieste to Venice, summing over those the lengths of those little pieces. Now, in a space-time, we define an interval, so we can do a similar thing. One important difference is that this interval is not sign definite. So here I took the square root of this distance. It was positive definite, so the square root was uniquely defined. We would define it to be positive. Here, if the curve changes from being time-like to a space-like, then there will be some ambiguity how to calculate it. So we consider only the curves which are always time-like or always a space. In this particular case, we are talking about the subluminal observers. So these curves are always time-like. Therefore, this interval is always positive. Okay, so so in general, I will have to do a similar thing. In general, I will have some curve here, and then I want to divide it into little pieces and calculate the invariant interval between those. Take the square root and sum them over these little pieces. So this, and that I call it tau. So that would be tau for this. Calculated for this particular curve that goes from point, I don't know, E, call them again T and tau T. Now let's consider the special case of Alice, which is moving with constant velocity. So again, we want to break it into small pieces and calculate the length of this. Say at some constant time t. So we want to calculate the length between here and the initial time when they meet, when these three observers met one another. So let's look at one of these small pieces. That d tau squared is just given by this formula for some little piece in here. And that is equal to what? It is dta squared minus dxa squared. So I don't need to put index a on t, so these are just 2 points here. So this is some small interval dt. But when we say that velocity of Alice is VA, that means that dxa dt is equal to VA, and that is a constant. And this is the time, the interval calculated for the board line of Alice. So from here I can relate dxa to dt, VA dt, which means that eta a squared is equal to dt squared times 1 minus VA squared. So since VA is less than 1, this is positive definite, so I can just take the square root and find eta A to be dt 1 minus VA squared, sorry, the square root of that, also known as the boost factor gamma A. And okay, now this VA is constant, and therefore it's summing over this DTAs over the board line is easy because this is a constant, so tau A is going to be just T over gamma A plus some integration constant. So for this time-like observers, this length, invariant length of the curve that I calculated in this way is got proper time. So this is the relation between the proper time of Alice and the coordinate time t, which happens to be the proper time of B, Bob. Right? If I consider the same calculation, but for Bob, since the velocity of Bob is 0, I get tau B is equal to T. So T is what Bob's clock measures. Any questions so far? Yes.
In general, the velocity is time dependent, right?
Yes.
Yeah. So.
Yes. Yes. So this is a special.
Yeah.
So up to here, there is no problem. You can divide it into infinitesimal pieces. There will be a relation, instantaneous relation between tau, t, and velocity. This part is special. Okay. So now it's time. Now it's time to ask a question. So we want to define for velocity. So the for velocity is defined. Now here I'm in 2 dimensions, so it's, this 4 is just metaphoric. But in general, for a curve, for a board line, we can define a for velocity. The idea is similar to here. So let's consider this example again. So we had this road going from Trieste to Venice. Now there is this is a curve. This road is a curve on this plane. On any curve, we can define a tangent vector. And since we have a notion of a distance, we can also normalize it. So we can talk about a tangent vector, which is a unit tangent vector. So this for velocity that I'm going to talk about is essentially a generalization of that to a space-time. So that is defined as dx mu divided by derivative of x mu with respect to tau, the proper time. And the question to you is that what is UA mu, eta mu. And then we want to ask what is UA mu, UB mu, eta mu. And then UA mu, UB mu. Okay, let's first do let's first do this.
B, do you mean bi square? B, it means bi square.
Oh yes, yes. This is the A square, and this is gamma of A square. says A, gamma squared, V squared. Who says minus 1? Okay, almost all. Who says none? Okay. So how do we can someone show it? Should I ask? Can you come and show?
Yes, I can.
Thank you.
Okay. X A mu is equal to T, and I have that vector X A, 4 vectors. So tau, and we calculated before, should be gamma, and this should be gamma times VA. Now if we take the derivative and this, if we change this to the VA, then we have it.
dt becomes
Yes. So now,
Can you write it? Just write how you get it.
how did I get it?
Yeah, this gamma VA. Just what you said, just write it down.
Okay, dxa by d tau, and I would like to transform it to dt. Then I would have it gamma times dx divided by dt. So that's
Thank you.
now we take this. When it's just a 4 vector norm, so it would be. I mean, if we plug this in, that would be, as eta is diagonal, so it will just be gamma squared, and we will have this square. So if we take gamma squared out, 1 minus a squared, and you have a minus here because of this, so we'll take the minus out here. And this is, these two cancel, and this will include minus 1.
Okay, thank you. Yes, okay, so as if explained, the x mu, or this is what we call UA, right? So UA mu is just given by gamma times 1 and VA, similarly for B and C. And then you can calculate these other quantities in a similar way using the definition of eta and these values. So for B, what we get is 1 and 0, and for C it will be just gamma C 1 and BC. So this UA dot UV is going to be minus gamma A, and UA dot, oh sorry, there is another thing, this invariant, this product is sometimes denoted by dots, the same way that, the same notation that we sometimes use for in the Euclidean geometry. So that's what I mean by dot. One can, another notation that we frequently use is that we lower the indices by the by the Minkowski metric. So this is another equivalent there, right? So the summation convention when we have Lorentz indices is that when we have repeated indices with upper and lower repeated indices, those are summed over. So here these mu's are summed over, here this mu, this mu. And then you can calculate this. Okay, the final part is that what would be the velocity of C as seen by A. So now what we want to do is to consider, instead of the velocities of Alice and Charlie as seen by Bob, we want to see what is the velocity of Charlie as seen by Alice. So let's call it V prime of, or let's call it VCA. So we want to see what is VCA. So this will be the last problem of today. Then we can go. So there are various options to calculate this. You can use the knowledge of the previous part. Or we can use the Lorentz transformations in different ways. So for instance, what would be the definition of Charlie's velocity as seen by A is equivalent to saying that we want to choose another coordinate system in which Alice is at rest, and we want to see what is the velocity of Charlie in that new coordinate system. So basically, it corresponds to finding the velocity of Charlie, finding how Lorentz transformation change velocity. So one way would be to look at the new coordinate system. So if we want to have, if these were the trajectories A, C, and D, x, t. So one way would be to find a coordinate system in which there is a t prime that is along the word line of Alice. So that would be a new Lorentz frame. And this is x prime, t prime, x prime. Find the Lorentz transformation to this new coordinate system and see what would be velocity of v in this new coordinate system. That's one way. Another way is to look more carefully at these results and see what would be VCA. So actually it's useful to write the result for it.
No.
None?
That was the
Okay. You are encouraged to discuss it with each other in pairs or groups if you like. Who says V C minus A? Who says B? Anyone C? What one then?
You're confused about the sign.
Well, I guess this cover all the possibilities.
So how you define VC and Is it written in vector notations? I mean, VC minus V. Is it a vector sum or just
Well, I mean,
algebraic?
I mean one dimension. So yeah, it's algebra.
Algebra.
Yeah.
Yes.
Okay, we can discuss it tomorrow at 11. Any questions? No, it's not B, C. Yeah. Yeah, I probably post the solutions to this today, just inside the lecture. And tomorrow we'll discuss Rinder observer and dynamics. Question?
So tomorrow is at 11, right?
Yes, tomorrow at 11.
Tomorrow is today, right?
Yes.
Which one?
He's not here as well, so
Yes, exactly. Where's the problem? Where's the they hold the
His definition is this definition is consistent.
Did you find anything about him? You're not gonna find anything.
he got to find a lot.
No, you're not.
Find a lot.
He's just geeky.
Yeah, he's as weird as you.
But smarter. You're still.
No, I'm normal, so you're weird.
You're normal?
Yes.
In his reference frame.
What upon the reference then?
So Lawrence invariant property?
He's a much less.
Lawrence invariant.
He's much less.
Would you consider just trading for skydiving?
What? Skydiving? Yeah.
Just-
Want to do it?
Yeah, there's a school nearby, and
Who will pay the money? How much money do I
I
have?
150.
I don't even have that money.
Not right now. I'm not.
Okay, in the summer maybe?
Yes, exactly. I'm not just not right now. 160 euros.
Okay, in the summer.
Yes, but 210 for them to film you or whatever. You will not dive by yourself. They will wear you.
I see.
There's a man that will love you.
Yes, yes.
No,
But 160 is a lot. I mean, what's the point?
160 is not a lot.
No, in Nepal it's $100. That's it.
He's going if
Okay.
going to
I checked it online and there's a lot of tools about this, but there are over 200 except this one, which is in Venice.
And we can die. Because it's the cheapest one.
I don't care.
Maybe we can do it after these courses.
Yeah, after finishing the standard model, I think we will be done. There will be like 1 or 2 courses. They will give us a course about these new particles that they were looking for. No, it's Susie particles.
It's super symmetry there.
Yeah, so they will give you the course, but not there is no
Grades, yes.
last year one was the same. This year one of the
No, that's it. Oh, this is. Oh, that's it. Same here.
Okay, so now. Okay, so how should we write this homework right now? Just the one page.
It will
So writing, yes, writing the answer in the small box. Yeah, I know, but he will. You can look at. Yes, no, the same line.
Yeah, no, you just write.
you know the answer to the first line or the last line? You can do the calculations.
You don't have to do it.
Just have to
You
understand.
know the reason.
Oh, yes. I know. What is the and just you have to recommend it. You have to hey, where were you last month? Where were you last yesterday?
Yesterday, no, I went to the yesterday I went to the library.
And
I'm so tired.
no, why didn't you come to the? I was waiting for you.
Really?
Yes.
You went with the guys, man. I was like a native waiting for you.
No, I waited for you.
You didn't talk to me.
Okay, you have
I have what?
the. Yeah, that's no problem.
Yeah, I have.
By the way, did it help?
Yeah, thank you.
No, it's
It was
just.
it wasn't a great difficult debate.
Yeah, 2 days ago I went to the gym and then went.
Yeah,